All right, so thank you for the introduction. So I'll be presenting this topic. In a moment, I'll be showing you a demo where we made a versatile configurator using first-order logic. So this demo was built entirely using generic tools that were already present at the university. So the first is our IDP system, which is the declarative system developed at KU Leuven, and its interactive consultant, which is its default user interface. So often, a lot of ad hoc scripting is still required to get to the point where we can use these tools. And our goal here is to reduce the amount of work for a user to get a working application. So if you look at our interactive consultant, we see this is the web shop for laptops. And so there's a lot of choices a user can make. So say a user says, I want my internal memory to be maximized. So if you do that, you see that internal memory goes to 32 gigabytes. And from the original 60 laptops, you can see next to the product code, only 4 remain. And if we look, our system also has propagated that there will be an SSD. And if you open the drop-down menu at brand, we see that only 2 brands remain. So it will be a Dell or a Lenovo. So far, so good. And say that we further want a laptop that's as small as possible, so to be practical, to take on a plane, for instance. Then it will say that the display diagonal is 14-inch, and it will further fill out the options to give you the product that you want. So this is great. This works. But how is this powered? And if we look, it's powered by the IDP system. The IDP system is a declarative system, as I mentioned. What's unique about this system is that it clearly follows the knowledge-based paradigm, which means that there's a strict separation between the user knowledge, so our knowledge base on the one hand, which is the cylinder f of dot in, and our inference engine on the other hand. So the inference engine is based on Microsoft Z3 and is able to carry out different inference tasks. But our knowledge should always be completely separated from that. So if we write our knowledge base, we don't know upfront what the laptop knowledge will be used for. Now use it to power a web shop, but it could be anything really. So f of dot, then when I talk about the IDP system, I'm talking about the full system. When I'm talking about our knowledge base or f of dot, I'm talking about the language that's actually used to write down our knowledge. And this f of dot is just first order logic with extensions. So the extensions are inductive definitions and types. So what does it look like? This is a simple map coloring problem. As you can see, it has 2 types, type color, type country. It has a predicate border and a function color. So then in the structure, we define these by enumeration. So you see this is a partial model of the world, so there's no definition for color. And in our theory block, we are able to add constraints such that if 2 countries are neighboring, then they have a distinct color. Finally, there's a procedure block, which is an optional block that's used to, if you want to run this directly, you can tell what inference task you're actually expecting. So here will be a model expand. And if you pass this to our inference engine, it will be able to give you a completely colored map. Or if you pass it to our interactive consultant, and you, for instance, select that Belgium should be red, then we'll immediately be able to tell you that since Belgium and the Netherlands share a border, that Netherlands cannot be red. So I've explained our interactive consultant. I've explained IDP. So we now have the working blocks from what was already there. But up until now, to get our knowledge into the system, we used ad hoc scripts. So users came to us with a bunch of knowledge. We manually created a knowledge base, and used this to work. But when I asked my colleagues, does anything exist? Everyone had written at a certain point, a script to transfer tabular data to f of dots. So I thought, can't we study this from a more logical perspective? Can't we derive a logical vocabulary automatically and transform our data to this logical structure? And if we have this, can we also use this to combine data from multiple sources to get a working application? So that's exactly what I set out to do. And that's why we introduced our knowledge base API for Python, or KeBAP for short. So as you can see, we have a bunch of input languages. input paradigm. Like if whatever you can create more inputs. For instance, we're also looking to translate RDF triples. Once you pass them, we go to a language agnostic logical specification, which we can then add or remove predicates functions from, or merge with different specifications. And then we can pass them to solvers for different languages. And since we were able to rely on some prior work, we even have partial ASP support for that. So I've introduced a problem. So now the remainder of this topic, for this talk, I'll basically be going over like what are the different steps to go from a table to an FO dot specification. And we start with this very simple example with students and courses, and students have a grade for a course. This very simple problem is very easy to translate. As you can see, each column represents a distinct type. And the possible values in the structure for this type are simply the set of values occurring in this column. Great, so this relies on 3 assumptions. Same identifier means same real-world object. So the programming course in row 2 and row 5 is the same programming course. And the unique name axiom, programming and maths are 2 distinct courses. And the closed world assumption, there aren't any courses that are not listed in this table. Do these assumptions always work? We figured like from numerical data that might not be the case. Because for instance, if you look at our grades, we know in Belgium, courses are graded on a scale between 0 and 20. But no one, for instance, scored a 20. So if we want to, for instance, say like a perfect student is a student who obtained a 20 for a course, we have a type mismatch. So what we decided to do for numeric types was use the built-in types. If they're all integers, we use ints. Otherwise, we use a floating point number. As you can see, that's not exactly what happened here because I do have a type grade, and it's a subtype of integer, and it is a range between 0 and 20. I was able to add this with a single line of code, but this is something that a user would have to add manually, and I'll show later how this is done. Yeah, my previous example was very simple. There were no overlapping types. But what happens the moment I add the same value occurs in multiple columns? So here we have 3 possible solutions. We just consider them as distinct types. But this will not work with our system because our system assumes that distinct types have no overlapping values. So this will give an error. On the other hand, we could consider that both these columns to be part of a single type. So both student and tutor could be seen as a person. So yeah, this option is also not ideal because now all our functions are partial functions and we lose the information that what values occurred in which column. So what we actually did was we implemented this as a supertype. So as soon as 2 columns have partially overlapping values, of course, if they're fully overlapping, we can simply say they're a single type. But if they're partially overlapping, we create a supertype, and each of the subtypes of a column will be, so each column will be a subtype of the supertype. The great thing about this is now we can use this subtype as for our default functions. So we keep the benefit of having total functions, which makes dealing with which makes writing specifications like theory constraints for this a lot easier. All right. So we also considered the alternative of using namespaces, but when you're dealing with a single table, you don't want to create separate namespaces for information coming from the same table. This didn't seem to make sense to us. All right, so now I've talked about the types, so columns, but of course we need to be able to talk about the rows of a table as well. This we can simply do by introducing functions. A function will take a key, and all columns that are not key columns will have a function that will map these key columns to the type of the non-key columns. So for instance, we have our grade here. So we have our grade uppercase, which is type, and there's a grade lowercase. So every student and course combination should be unique. If there's a single column as a key column, of course, that's not an issue. There's no requirement that they should be complete, just like they have to be unique because, well, otherwise we can't distinguish between different rows. So I think that's obvious. Our tutor example, which I showed earlier, like a complete function, and our earlier example is also an example of this. So where do we get, then the only question is, where do we get these primary keys from? So now since student and course are the first two rows that combined are unique. But the easiest is just ask the user. Makes sense. But we also wanted an automatic way to do this. And there are three options to do this automatically. First, you just take the first X columns until you get unique keys. But this is a bit of a gamble. Like in our perfectly curated example, it works out. But what if I had set tutors as a second column instead of course? Now we have these very weird combinations, and it just doesn't make sense declaratively. We could use a single predicate, but as soon as our tables grow larger, like our laptop example has over 50 columns, just gets unwieldy. So default, we just use an index. We introduce an index, nothing to care about that. So with this information, we have enough to actually see how this very simple demo, because I mentioned like we're trying to get this to work in Python, how we can use our KeBAP tool to actually go from our table to FO.specification. And the other thing that's really, so the first thing I have to mention is we have this configuration where I set that grades as a type grades and not the default integer. So here I overwrite the default. Here this is actually what I'm doing. I'm saying like I have a file which is my my CSV, my grade CSV. This is the language. The origin is a CSV. We have this configuration file. This configuration, which is a nested dictionary in Python, but could also have been a JSON file. And we have our keys. And that's enough to get this very simple demo to work. And then the final row is just like, I want to print it out, translate it to IDP33 and print it. Of course, I showed you this laptop demo at the start, and now I'm talking about this very simple example. So there's probably two issues that people are still worrying about. Like I mentioned that we can combine different specifications. So how do you do that? And the second part is, of course, real-world data has missing values. How can we deal with that? So I'll deal with each of these in turn before I end the talk. OK, so the first, merging specifications. So we have actually our laptop demo had two files. So there's laptop data and there's the CPU data. So if we want to merge these, again, we have an issue of partially overlapping types, possibly. Like there could be CPUs in the one file that are not in the other. Actually, we can use the same solution for that if the same type had occurred in multiple columns. So we can just create a super type. This is the default way of dealing with that. And then there's a possibility of name clashes, like for instance, if a function, if identical functions exist in two files. But the risk of that is rather small because the laptop data will have a laptop key column and the CPU data has a CPU. So they have different keys. So the chances of them actually having functions that deal with the same problem are rather small. So if this does occur, this is something that the user will have to deal with. It will just throw an error. OK, so our laptop demo, how is it construed? So we have our CSVs for laptop data. We have CSVs for processor data. We pass these. We get two specifications. We can simply merge these together into a larger specification. So there's also alternatives of leaving them separate and having them actually to have your data decentralized and having your data interact with each other. But this is future work. So this is something that would actually be interesting to look into, but we haven't done yet. Then we can add our standard configuration and constraints. So what's going on here? If I were to pass this specification to our interactive consultant, we just give you a blank screen. Why? We have a complete specification. There's nothing to be decided. So yeah, everything is known, perfect world, no issues. But of course, we need to represent user choices. And for this, so I already introduced the type brand with a capital B and a function brand to represent a row. And now I'm also introducing a constant brand with an underscore, with trailing underscore, to represent the user choices. This underscore very conveniently gets automatically deleted by the interactive consultant, so it's not an issue. And now we can simply say that my brand type must be equal. So my brand constant must be equal to the brand of the chosen laptop. And this is enough for our system to be able to handle user choice. Now, of course, why am I doing all this? I now created this laptop demo. Now the interesting part, so now we can add custom constraints. These custom constraints, for instance, like now we have this very flexible web shop, and if I were to say, I want a user to be able to select if he's looking for instance, for a gaming laptop, then I can simply write a constraint that says, if gaming laptop is a laptop that meets these specifications, I don't need to add the column to my CSV and manually check these. Our system will handle this. And if at a later point in time, the definition of a gaming laptop changes, we can simply update this one line of logic, like this one constraint, and the system will still work as intended. So after we add that, we can pass it to the interactive consultant. We can create our custom user interface, which we will most likely do. Or we can just pass it back to the system for further manipulations. So the sky's the limit. And so this is the entire code. Well, it's slightly abbreviated. I abbreviated configuration, which I put in a JSON, actually, in the real application, to create our laptop demo. So this is just like, this is just variables that tell me which files exist, and there's a configuration. This you have actually already seen, but with a simple example, but here I do it twice, just once for both files. Then there's a merge function. I add my default constants, and I translate it, but here I don't print it, but I save it to a file. And that's all that's going on. So in these few lines of code, I'm able to transfer my tables into a fully functioning application. But of course, there's the one thing I still have to mention, missing values. So here in this example, there's only a tutor for the programming course. Again, there are three options. But here we just introduce a partial function. So my tutor function here has a domain tutor definition, and this tutor definition is a predicate that just tells me where tutor is defined. We considered alternatives, so requiring a default value, and this is actually what I do in the laptop demo. I provide defaults, but defaults are not always useful. Or we could use the superset symbol, like for our enumerations. We also allowed to use a superset instead of a definitional equality to say that we only give a partial enumeration. But there's an implicit assumption here that missing values do exist. For instance, for the weight of the laptop, this makes sense. Every laptop has a weight, whether it's known or not. But there are consequences for propagation. Like, for instance, our interactive consultant will never be able to delete these laptops. So if you say the weight of a laptop has to be as low as possible, all laptops that don't have a weight will still be in there because it will just say, like, I don't know, I have to delete them or not. And if you have a model expand, it will add a value, a possible weight for a laptop. And this weight might or might not be correct. So in the one case, I say, like, for instance, my laptop has to be lighter than 2 kilos. In one case, if I do a model expand, in some models, it will be. In other models, it won't be. This is not actually what we want. And with our partial functions, even if we do consider that all laptops do have a weight, so partial function is actually not entirely appropriate, the predicates, the automatically added predicate that says where it is defined, is actually still useful because that predicate can be used to, let's say, like, I want to be sure that my laptop is lighter than 2 kilos. It's a hard constraint. I can actually just say, like, and I only want to take into account these laptops where weight is defined, and it will just remove the other ones. And thanks to our automatic default, our choice constant creator, these choice constants will also automatically be created. So in conclusion, I've introduced KeBAP, which aims to reduce the amount of preparatory work required by users to enter data into our system. It's a flexible framework that also allows for many future extensions. Allows to introduce, as I mentioned already, we can introduce additional input paradigms, or we can create further functionalities such as allowing decentralized data instead of the monolithic data which we use now. So that was my talk. Thank you very much for listening.
Okay. Questions? Yes.
So part of your work reminded me to something called bidirectional transformations. I don't know if you're aware of that. In these bidirectional transformations, you typically consider two representations of the same data, as perhaps you do, like a logical representation and a database representation. And then you have a couple of functions, get and put, to go from one direction to the other. And these functions must, there are a number of laws that must hold, the get put, put get, and so on. There is a number of laws to ensure that everything goes fine. And the nice thing of this framework is that allows you to keep both representations synchronized, which I don't know is something you are interested. So that if you change something in the database, you can automatically propagate this change and vice versa. Directly applicable, but perhaps you can find some useful ideas in these bidirectional transformations.
Because I forgot to mention it, but as you can see, like after we propagate our data, like after we do a model expand, for instance, we of course also want to reintroduce these this output into our system, so get it back to the language independence representation. So thank you for that information, for the hint.
I'm not sure if I understood correctly. You said that your type names correspond to the headers in your CSV files, and you're making the assumption that the same header doesn't appear in two different files? Did I understand? Is that only because you're using a very small number of files? It seems like you're very likely to have name in 1,000 different files as a header, even if it's not the name of a person, name of a vendor, or name of a city, or whatever.
We make the assumption that the same header does not occur multiple times in the same file. It only becomes a problem if it occurs in multiple files, if you actually want to physically merge these files, which sometimes you might want to do. Like for instance, in our processor example, the one was called product code, the other was called processor. So it didn't make a difference, but both of them could have been called name. So that could have been an issue, and then you have to actually manually, at the moment, you actually have to manually rename one. But as soon as we go into, like in the next step, I really want to look into this decentralized data, and then that will no longer be an issue, I think. Might still. At the moment, I only support the tables. Yeah, so no nested tables.
Another question is, so
But no, the order of the rows doesn't really matter for the system. So just like it just extracts them like. Yeah, so for instance, so here just like, if for instance, all the programming scores were first introduced and ending, so it just translates to this, so it doesn't really matter.
of course, if